Hello everyone, I am Edgar Trapulli. I'm currently doing my studies at Facultad de Ciencias Biológicas in BOAB, and today I'm going to be talking about cellular excitability, electrical elements of biological membranes, and action potential. There are different things in nature that resemble to the things that we can see on the environment. Electricity is one of them, and when it comes to talk about electricity, we refer to Hodgkin and Huxley, because they formulated their theory of the action potential. It was 50 years ago, and it remains one of the great success stories in biology, and it ranks among the most significant conceptual breakthroughs in neuroscience. So, as an objective, I have to describe the cellular elements that allow biological electricity and the generation of the action potential. For understanding how biological electricity happens, we must consider that in neurons, in cells, there are different environments inside and outside the cells. Here you can see the concentration of the ions outside the cell and the concentration of ions inside the cell. So there are different concentrations that establish a electrochemical gradient, establishing voltage in a membrane. There are other elements that allow the currents to pass through the membrane. Those are the channels. We have open channels and voltage-gated channels. And the electrical current passes through the different ion channels. And what's important here is that current is carried out by ions. And even though both intracellular and extracellular space are electrically neutral, a small difference in their concentration, in the concentration of ions, is enough to establish a membrane voltage. And, we can actually describe the electrical behavior of a cell in rest with an electrical circuit. Here we have it. In this circuit, we represent the membrane as a capacitor, the voltage-gated channels that have a non-linear behavior, and the channels as batteries. And when voltage values move away from resting voltage, subthreshold responses such as EPSP1 or EPSP2 or even action potential itself may be displayed. Now let's talk about action potential. In general, there are three phases present in time: a depolarization phase, a repolarization phase, and a refractory period. Here we have the scheme of the action potential. This is the actual record of the action potential in the giant squid axon from Hodgkin and Huxley experiments. And on this side, we have the representation of the action potential and all the currents, all the conductances that made up the action potential. Also here you can see that ions themselves have a resting voltage. Ions are always passing through the membrane, but certain values of voltage, ions have no net flux. And knowledge about the action potential electrophysiology is useful for medical research purposes. For example, it has been reported that sodium and calcium channel behavior is affected by botulinum toxin A in red cardiomyocytes, And well, this toxin can be used to treat postoperative arrhythmias. Here you can see the representation of the sodium and calcium currents. And when using the botulinum toxin, those currents are inhibited. And well, as a conclusion, I'd say that loss of electricity can be applied to biological phenomena. In organisms, electricity is crucial for cellular communication. And well, something curious about the action potential is that thanks to this squid, to the giant squid axon, and to the voltage clamp technique, Hodgkin and Huxley were able to describe the action potential. Well, that's going to be it for today. Thank you for watching, and have a good one.